so far we have seen Ethernet frame, correct, with all the details about all the fields, right? That is standard Ethernet especially. Now before going to other Ethernets, we will see various models we can connect the systems in Ethernet. One is having bus topology. This is bus topology, correct? But there are other topologies possible, and if you use that topologies, then definitely performance will be increased. We will see. First of all, we start with basic model. We used to have this one, right? Now assume that, let's say this channel capacity 10 Mbps, okay, otherwise usable. So we know that in Ethernet, though your bandwidth is 10 Mbps, you can't get it, right? Why? Because of the collisions and all. So that effectively you can't have 10 Mbps, correct? Assume that, let's say after collisions everything, then this is, let's say, usable bandwidth, let's say 10 Mbps. Either we think like that, otherwise we can go with this model. So let's say there is no collision, we are going for a best possibility. Assume that, let's say channel is lightly loaded so that there is no collision. That means systems are not parallelly trying. Okay, why sir that assumption? Simply I want to focus on other issues. I don't want to focus on these collisions and all. Okay, either go with this model. What? Assume that this 10 Mbps is the bandwidth of the channel after considering all the collisions. Second one, assume that there is no collision. Okay, anyway, finally you have 10 Mbps usable bandwidth. Okay, now A, B, C, D, E, F, if they all equally trying for the channel, then obviously since this 10 Mbps is common for them, correct? So definitely that bandwidth will be divided among all the systems. That is what I want to say. Yes or no? Example, let's say there are only two systems and there is a medium, common medium. Then if A sends, then B cannot send. If B sends, A cannot send. And this is, let's say 10 Mbps channel. Then definitely, so A and B cannot send 10 Mbps per second. If A sends, then B cannot send, right? Assume that, let's say they are equally sharing the channel. Then overall A and B together is using 10 Mbps, correct? How can you have more bandwidth than the existing channel's bandwidth? Understand? Example, this is a water pipe. From this, A and B are using the water. In the overall tank, there are 10 liters. Then A and B together can consume only 10 liters, not more than that. Okay. Don't say that, sir, if there is a pipe, this is a tanker with 10 liters. What if A opens a pipe here and B opens a pipe here? Yes. Still, you can't get more than 10 liters, isn't it? In the same way, when there is a 10 Mbps bandwidth channel, since A and B are not parallelly using it, so overall I can say that effectively at most 5, if they equally share, then 5 Mbps and 5 Mbps. In that way we can divide the bandwidth. Similarly, here also if 10 Mbps channel we have and 1, 2, 3, 4, 5, 6, if there are 6 computers or devices, then on average, so each system is going to have at most 10 by 6, correct? That means I am equally sharing the bandwidth. Then 10 by 6 Mbps system A can have. In the same way everything. Now if everyone has 10 by 6, 10 by 6, 10 by 6 Mbps, that means, so what happens, we'll see. Try to add them. If you add again 10 by 6 plus, if you sum all the bandwidths of A, B, C, D, E, F, then you get again 10. Yes, because that is the original bandwidth. And sir, we didn't get why it is 10 by 6. So here one assumption is every station is equally using the channel. Okay. Now one overall example, let's say we observe this for 1 hour, then you will understand. Let's divide that 1 hour into 6 parts, 10 minutes, 10 minutes, 10 minutes, in that way. Assume that, let's say A is using 10 minutes, after that B is using, that's why there is no collision. This is the best model. So if A uses this one, then that 10 minutes of time, what is the data rate A can have? 10 Mbps. That means it is going to send data with 10 Mbps bandwidth. Now question number 1, what is the, otherwise, what is, how many bits this A is going to send in the 10 minutes? We will calculate. 10 minutes means what? 600 seconds, correct? So let's keep 600 seconds into, in each second we can send 10 M, right? 10 megabits. So 10 megabits. Finally 600 into 10 megabits, remember it. Similarly, in next other 10 minutes, B is going to have 600 into 10 MB. That means these many bits it can send in that way. So everyone is going to send this much data. Okay. Now let's sum it up. If you sum it up, then how many bits all over all these A, B, C, D, F are going to send? A 600 into 10 MB plus B 600 seconds into in each second 10 MB. In that way 6 times, correct? Let's write, that's why 6 into 600 into 10 MB. This entire thing in how, so this is the data, right? These many bits they sent overall, but in how many hours? In 1 hour, correct? 1 hour means what? 60 minutes. Minute means 60 seconds, correct? Now let's simplify it. 6 10 there. Now see here, 600, 60 into 10, 600, 600 cancel. You got 10 MB back. That is what I said. Finally, you can't use more than 10 Mbps. So if equally the bandwidth is divided, that means if they share the channel with the time, of course it is theoretical idea. I'm not saying that in Ethernet it happens. I'm not saying that. I'm saying that, so we are just thinking about mathematical possibilities. Like, if really they have data requirement like that, first 10 minutes A is using the channel randomly. I mean, it's not intentionally, but let's say if it happens. So B 10 minutes, C 10 minutes, D 10 minutes, E 10 minutes, F 10 minutes. Then in this entire 1 hour, this much data they transferred. That's why then what could be the bandwidth overall these computers are using is 10 Mbps, right? So now remember one thing, one blind formula. Whenever you have a 10 Mbps channel, then if we assume that everyone is equally sharing the channel, then 10 by 6 bits, I mean megabits per second they can send. Sir, how speed will be reduced? Because how speed will be reduced, I will tell you. Whenever they send with 10 Mbps speed only, but they don't get always the time, right? It will be like this. I talk about only A. Okay. So assume that, let's say in 1 hour of time, A is doing like this. 10 minutes he is using the channel, but 50 minutes he is not getting the channel, let's say. So in 10 minutes, what amount of data it is going to send? We will see. 10 minutes means 600 seconds, right? So 600 seconds of that time, what is the bandwidth? 10 Mbps. So this 600 seconds, it is going to use full bandwidth, 10 MB. Okay, plus, but remaining 50 minutes of time, because of this, bandwidth will be reduced, 0, correct? So no transmission overall. If you take the average, what happens, we'll see. 600 seconds into 10 MB plus 50 minutes, of course 50 minutes means 3000 seconds, whatever it is, into 0, right? This overall is 0. Overall per 1 hour. 1 hour means, again if I convert it to seconds, it will be 60 minutes. Minute means 60 seconds. Now let's simplify. You got 600 into 10 MB by 60. 600 into 10 MB. Let's keep 10 MB as it is by 60 into 60. So 60 tens are 600. 0 will be cancelled. You get 10 MB by 6. That is what I said. Finally, if they equally share, everyone gets 10 by 6th of MB. Understand? Now, if we connect the systems in a different way, then you can increase the bandwidth. That means finally, what is the problem with Ethernet is, if the channel's bandwidth is 10 Mbps, so every station is getting only 10 by 6 in the best case, right? I'm assuming no collisions, and already I told you the model, right? Now, what we do is, we use bridge. Using the bridge, if I connect the systems, then we are going to have increase in the bandwidth. How, sir? We will see. So here, this is the connection, otherwise the model what we are using for connecting the computers. Let's say you have again same 6 computers, A, B, C. Here you have 3 devices, D, E, F, overall 6, right? What you do is, first of all take 3 systems and using the Ethernet, so using the dash topology, bus topology, you connect them. Now again take 3 systems and using the bus topology connect them. So here we are implementing Ethernet. Let's say Ethernet 1. This is Ethernet 2. So in between we are keeping bridge. I will tell you, properties of bridge in a clear way and in a depth way. At this moment, let's try to understand what bridge is going to do. Bridge can, whenever frame comes to bridge, it will observe the destination, and if the destination is at right side, example, let's say bridge functionality is like this, it's forwarding. Bridge functionality is forwarding. Whenever a frame comes to bridge, so this is called port. This is port 1, port 2. Whenever any data comes from any port, like example, let's say one frame is coming like this, okay, from port number 1, then it will be received by your bridge. Then bridge will see the destination address, and if the destination address is at right side, sir, that means bridge knows that which computer at which side. Yes, so bridge is going to maintain a table with two things: port number and corresponding destination addresses. Port number and corresponding destination addresses. In that way, so destination address of D, E, F will be maintained by your bridge. So what that bridge is going to do is, so it's a software, bridge is a device, it will have software. Using that software, this table will be maintained. We will see that details at this moment. Assume that, so whenever destination address is seen, bridge is mapping like this. Okay, D, where is D? Port number 2. Automatically this side data will be sent. Now you see, again it's again Ethernet. Whenever some frame comes to Ethernet, we know the model, right? So that signals will go like this, and D and E, F will sense it. That means they will observe it, and the right person will take it. If any frame comes from this side, then what happens? You see, example, let's say some frame is coming from F and it is towards C, then it will hit bridge. Okay, so bridge will see the destination address and it will see the table. Based on the table's values, so it will send to port number 1, otherwise it will discard. Example, let's say F is sending a message to E, otherwise D. For that, it will come like this. Of course, since it is from F to D, D will take it. After that, we know that signal will propagate like this and it will come to bridge through the port number 2. Then bridge will take it and it will see the destination address, and it says that same port, whatever the way it come, so the same way we should return. But why to return, right? Bridge is an intelligent device. So what it will do is, so it will understand that already the destination has been reached, so it will simply discard that frame. In that way, so bridge effectively separates two LANs, I can say. Okay, so what is the advantage of that? We'll see. Here we know that it was 10 by 6, correct? Everyone was having almost on average 10 by 6 bandwidth. If same 10 Mbps cable if we use, otherwise the channel capacity is 10 Mbps, then what is going to happen is, so that 10 Mbps here and 10 Mbps here. We know that, so the bandwidth comes because of the cable's properties, right? And the system properties. So that's why I can say that mainly this channels is built of, let's say, copper cable, and that copper cable will have some bandwidth capacity. That means how many signals it can say take for a second. Based on that, bandwidth will be dependent, not based on the length of the cable, right? So that's why, so this channel's bandwidth is 10 Mbps, here also 10 Mbps, but here only 3 people are using. Then I can say that on average, so everyone get 10 by 3 Mbps bandwidth. Sir, then we can have another idea. What is that? Why 3? Why not 2? Yes, you can go for that model also. We will see that. Now we'll see this example. Here you have LAN number 1 and here LAN 2 and LAN 3. Okay. So we have 3 systems here and 2 systems here, 2 systems. So finally 7 systems has been connected, and these two are separate LAN, separate LAN, separate LAN, correct? So bridge is now connecting these 3 LANs. Now what happens, we'll see. Example, let's say station A wants to send a frame to station B. So simply A will keep that frame here. It will go like this. Okay. So meanwhile, because it is connected to switch, then it will go like this. Then switch will take it and it will see the table. In the table, there will be information like this. Assume that, let's say, it knows that B is at port number 1. So whenever A writes a frame, on that frame one thing, right? How A is writing the message or frame. So A's frame will be like this. In that frame, let's call F. So destination address will be B. Such frame, when it is received by switch, it will see destination 1, see this B and this B matches, then port number 1. Now it will see like this. It is coming from port number 2. Now it has to go to port number 1. Simply it will forward it. Okay. So in that way, switch is an intelligent device which can, send frames from one LAN to another LAN. Okay. Now if you see the bandwidth, same 10 Mbps, 10 Mbps, 10 Mbps if you have, then here each one is getting 5 Mbps. In that way, so everyone's bandwidth individually has been improved, isn't it? So that is the advantage of switch. Correct? Also known as bridge. There is a small difference between bridge and switch. We can say bridge or switch interchangeably, but usually switch is actually a bridge with n ports. Okay, what is the difference between switch and bridge? If you want to know, there is no much difference. We can use them interchangeably, but strictly speaking, switch is nothing but actually multi-port bridge. Usually switch contains many number of ports. Okay, because of that, what can we do is, so we can go for switched Ethernet. Now try to understand what is switched Ethernet. Rather than connecting even two systems to a LAN, we connect only one system to the LAN. Example, let's say you have 8 computers or devices. So don't create two system LAN. When you do that, unnecessarily bandwidth will be reduced, right? So that's why what we do is we take a switched Ethernet. That means we are going to have a switch. It will have 8 ports. Let's say, assume that let's say it has many number of ports, 1 2 3 4 5 6 7 8 and more also. So what we are going to do is, so here to here, let's say this is a cable. Through cable we connect it to system number 1. Okay. Now here system number 2, in that way. System number 3, system number 4. So system number 5, system number 6. Did you remember here? So here we are connecting this bridge. Was having now how many ports? 1, 2, 3 ports, correct? But now this switch is having any number of ports, like usually very huge number of ports. That's why, so we can easily connect all individual systems directly to switch. Okay, no LAN now. So this is actually switched Ethernet or switched LAN. So what happens, we'll see. Now there is no collision. So far in all the previous examples, there is a collision, right? First of all, we started with a LAN with many number of computers or devices. So collision domain was big, very big collision domain. That means any two systems start sending, there is a collision, right? When collision domain is divided like this, let's take here switch or bridge, whatever. We can use interchangeably, switch or bridge. So this is port number 1, port number 2. What I want to say is, imagine that there is a system A, system E, and here system C and system D. Whenever A wants to send data to E, at the same time C also wants to send data to D, there is no problem. There is no collision. But if this is one common, I can say, collision domain, there will be definitely collision. But here now A can send to E, C can send to D simultaneously. That's why I can say that, so dividing the collision domain will be always good. Now in switched Ethernet, there is no collision. I will tell you the reason. Because no two systems are sharing the medium here. Every system is having direct connection to switch. Now, how this, in switched Ethernet messages will be transferred, we'll see. Example, one is sending some data to 2. So that data will be transferred like this. First of all, it will go like this. So it will reach to switch. Switch will store it first of all. Switch will have a buffer. Why? If there is no buffer, then if it simply relays it, okay, without buffering. So what can happen is, what if one wants to send to 2, 2 wants to send to 1 at a time? So what is going to happen, you see. Let's say 1 is sending to 2, at the same time 2 is sending to 1. There will be a collision, correct? So how to avoid it and how switch is going to avoid it, I will tell you. Here we are going to have two-way communication. This is called, full duplex. So whenever we implement switched Ethernet, so especially every system is connected to directly switch, then we use full duplex lines. Okay, full duplex communication. That is one modification. If you do that, then we can avoid the collision. How, we'll see. So here every system is going to have one incoming path, one outgoing path. That means whenever one wants to send data to outside world, then there will be one path, one channel. So there is another channel for receiving the data. Because of that, there is no collision, you see. Example, let's say one is transmitting to, one is sending to 2. At the same time, let's say 2 is also sending data to 1. What is going to happen, we'll see. So 2 is also having 2 lines, okay. One is incoming, one is receiving. That's why one small assumption here is, so far we assume that, so our Ethernets are half duplex. That means, so we have only one common cable for receiving and for sending. So such kind of communication is called half duplex. That means such computers were not able to send and receive at a time. If they send and receive at a time, they get collision, right? So that's why, so I can say that so far whatever you have studied, in that we had only half duplex transmission. Now I am extending it to full duplex transition. So if you have full duplex like this, multiple cables, what is going to happen, we will see. Now we'll see this switched Ethernet. So here there are 4 ports and 4 computers or devices A, B, C, D, and each device is connected to switch, and there are 2 channels, I can say. One is incoming and outgoing. That means at a time A can send the data and receive the data. So such a way, it's of course costly, but if you compare with half duplex transmission, so this is full duplex. Our assumption is full duplex system. Now there will not be collision. Why? We will see. Example, let's say A is sending a frame to B, B is sending a frame to A simultaneously. What is going to happen and why there is no collision? So here switch is a intelligent device. It is going to have a table, remember it. How it will maintain the table, I will tell you. So this port is numbered 1, 2, 3, 4 for our imagination. But how this switch is going to recognize them, that's a hardware thing. At this moment you remember that. So switch will have all the information. Who is connected to each frame, each port, 1, 2, 3, 4. So port and destination address. What is the destination address of port number 1? That means switch, in this switch 1 is connected to A in that way, 2 is connected to B, 3 is connected to C, 4 is connected to D. Now using this table, so the system admin will try, whoever maintain this switch, he is going to manually update these entries. Otherwise we have nowadays currently, so there are so many so many algorithms. I am going to teach one of the algorithm. So such algorithm can dynamically update this data. We will see the details at this moment. So it is static. That means whenever we configure switch, whenever systems are connected, then manually we write like this. We update this table like this. Port number 1 is connected. For port number 1, system A is connected. This is called statically filling the data. Okay. First we begin with static filling. So static switch, I can say. Let's do. Frame A is sending to B, B is sending to A. Let's begin. First of all, let's assume that simultaneously they are sending. Whenever simultaneously the frames comes to switch, so switch is going to maintain. So it's a hardware. Automatically they will be going to switch memory, that is called buffer. So switch is going to maintain a buffer. Through whatever the port data comes, okay, so that will be automatically filled into this buffer, such a way that hardware will be planned. Okay, now let's call this as frame number 1, this as frame number 2, and other details are unnecessary for us, but destination address of frame number 1 is B, destination address of frame number 2 is A, correct? Now frame number 1 is slowly coming and it will automatically will be buffered here. Assume that, let's say, a simple mechanism is switch is a a device. It will have software. It's like your computer. There will be software. So because of software and hardware, that functionality can be implemented. Whatever the functionality I am telling, listen carefully. So frame number 1 will be automatically buffered. Such a way it will have software. Next, at the same time, one more frame comes, then that is also going to the memory in that way. So through the various ports, data will come to this buffer. Okay. Now in that way, finally every frame will be buffered. Now we talk about frame number 1, frame number 2. So switch is going to process them one by one. That's why switch is called store and forward device. Store and forward. See, are we simply relaying it? In the earlier classes, I told you that there is a device called hub, right? What is the difference between hub and switch, we will see, but at this moment I would like to add one point to that. Hub is simply relaying device. Whatever comes to it, it blindly it sends, it relays it. If that happens, if it is hub instead of switch, what is going to happen? Frame number 1 will go like this, frame number 2 will go like this. So frame number 2 will be automatically relayed and frame number 1 will be automatically related. So how to understand hub, I will tell you. This is your cable and there is another cable. Hub is simply, I can say that it is tying it. Hub is a tying device. So that if data comes like this, data come like this, if this data will go this side, this data will go this side because of the hub, then collision will happen. That is a property of hub. Okay, simply hub can be imagined as I can say tying device. That's it. There are two physical cables, it will tie them, that's it. So that this data will go this side, this data will go this side. But switch is not such kind of device. It can store the data and it is going to process it. See, now what this switch is going to do, we will see. First of all, F1 will be processed. What is the destination address? B. Now it will look this table. Okay, so it is processing like this. B means 2. Then immediately, so using the circuit, that frame will be sent to 2. Okay, so it will come like this. Now there is no collision because, see, one more thing, we have separate line for incoming and outgoing. You never get any collision, correct? If and all if collision happens now, you should get collision now, correct? But why collision won't occur? Because the sending line of B and receiving line of B is different. So remember one thing, if you really want to have non-collision model, so the transmission mode should be full duplex. That means your medium should support full duplex. Supporting full duplex means what? Every device should have incoming separate and outgoing separate. Understand? Now, so finally F1 will reach here and F2 will reach this side. Understand? But we don't know the order. But remember one thing, there is a delay. It's not like hub. So here, if your switch has a lot of connections, then all the frames comes at a time. Buffer cannot, your switch cannot send everything at a time, correct? So because switch is one processor, it has to process every frame to send it. That's why I can say that switch takes some time. So there is a processing delay. So your operations will be slowed down. Understand? But at the what is the benefit? Now there is no collision domain, no collision CSMACD, everything, right? Remember, first point, when you connect your computers in this way, this is called switched LAN. In switched LAN or switched Ethernet, you don't require collision model or collision detection. So CSMACD is cancelled. No CSMACD is required. Understand? Now, example, let's say the cable's bandwidth is 10 Mbps. So everyone will have the 10 Mbps bandwidth. Understand? But one thing, there is a trade-off. So your frames will be buffered. So they will take some time and switch is going to observe them. Observing takes processing time, right? Already I told you while I was teaching you, delays, like what is propagation delay, what is transmission time. Now here switch is causing some delays. What are they? Processing delay. Second one again transmission delay, correct? So that you should understand. Because of that, it takes a little bit more time than usual LAN. Understand? But bandwidth is dramatically increased. Remember it. That's why, because of, see, there are a lot of variations. Remember one more thing. First of all, we started with, standard Ethernet. That was, CSMACD model, right? So there was a collision domain and it was supporting 10 Mbps. Usually standard Ethernet was supporting 10 Mbps bandwidth. Now, after that, there are other Ethernets also. I classified them: standard Ethernet, fast Ethernet, gigabit Ethernet, 10 gigabit Ethernet. All these things are because of the advancements in the technology. So we don't bother about remaining things. Okay. Nowadays, remember one thing, there is no CSMACD. But in the GATE exam, if and all if they give a question related to CSMACD, you should answer it. That means you should assume that the model is standard Ethernet, the bus model.